Okay, in the book, section 4.7 of the book, it takes 3 pages to explain this, force and couple. It's not that hard. Let me just say in words what they're doing. You have a picture with a bunch of forces and a bunch of couples. You want to get one force and one moment somewhere at the point O, let's say. Well, the resultant force, just add up all the forces. And the resultant moment, and this is what takes a little bit of explaining, the resultant moment at point O, just add up all the couples and add up all the moments about point O. All your forces are reduced to one force, and all your forces and moments are reduced to one moment. That's very, very nice. Section 4.8 in the book talks about simplification. But when I read it, it's not actually very simple. What they mean is take an expression and make it smaller. For example, this backpack here, it folds up into a pocket that goes like this, so you can have a backpack on your keychain for some reason if you've ever needed that. I wouldn't call it simplification. I would call it smallification, which is not a word, so if you want a real word, I would call it compaction. But I like smallification. It's easier for me to remember. Before we start our discussion of smallification, let's remember our 2 categories. We first started with particles, which were concurrent forces, and there were no moments. Right now, we are on our first discussion of rigid bodies, not a particle. We're doing this right now. If you've noticed, the forces don't all go through a point, and of course, what we're doing right now is learning how to deal with moments. The basic concept behind this smallification, I better quit saying that. Anyway, the basic concept is that a force and a moment can be replaced by a force without the moment at a special point. The book covers this in 2D, 3D with all the forces parallel, and a 3D screw and a 3D wrench. Okay, I'm going to quit saying smallification. Here's the strategy for 2D compaction. Smallification, so compaction. You have all these forces in A. You add up all the forces at a point, add up all the forces, and you get the resultant force here. And then you take all the moments about O, and you get this resultant moment. Then, if you move that force to a different spot here, notice that F times D will make a moment about O. This C is equivalent to B. Putting a force offset from O will be the same as putting a force at O and putting a moment at O. This is what we're calling compaction. I think it's more complicated, but we want to find a special point where you put the force that has the same effect. It has the same force and moment at O. Let's talk about this in reverse. When you use a wrench, okay, you push here on the end, and you know the reason you're doing this is because you want to put a moment there. You want to turn that nut. But what you're really doing to that nut, or let's draw that here. What you're really doing at O is, you're putting this moment, but I don't know if you've ever thought about it, you're also pushing that force there. So if I told you, I have a force and a moment there, if you reverse the process, you could say, that's equivalent to pushing at F at distance D away from the nut, or pushing on the end of the wrench. But what we have is you start with this, and I want you to tell me, where do I push to make that equivalent force and moment. Okay, here is 3D parallel force compaction. You pick an axis. You know how to take moments about an axis. You add up all the parallel forces and you get this resultant, and then you do r cross f dot unit vector, and you add them all up and you get this moment about an axis. Well, we want to get rid of that moment. We want to represent that just as a force times a distance, and you do the same thing. You move it a distance d away from the point O, perpendicular to that axis, and this here in C will have the same effect as a moment and a force at point O, here drawn in B. And finally, we have this 3D general screwdriver compaction. What you have, you start with a force and an arbitrary moment. Then what you do is you take that moment and you break it into a component like this and a component like that. Remember how a vector works is that a moment vector, you point your thumb along the arrow and you spin it around it. Well, when you push in a direction and you turn in a direction, that same direction, that's a screwdriver, right? Because when you're trying to, let's say, tighten this screw, you are going to turn it, but so that it doesn't slip out of the screw head, you're also pushing down when you turn it. There you go. That's this vector there, pushing with a force, and this moment vector here is right there. Well, in general, then you'll also have this weird wrench right here, this moment where you're turning it. Well, if you push on your screwdriver a distance d away, this force here times that distance there, let me draw it here, that force times that distance, that's going to cause this moment right there. So what you can do to simulate or be equivalent to this, you take a screwdriver where you are pushing, torquing, and this extra distance d here will also then give you a moment about the a-axis.